Okay, so today let's have a look at lesson 3 of chapter 2, second derivatives. So first of all, let's have a look at today's learning goals. After this lesson, you are expected to be able to understand the concept of second derivatives, then evaluate the second derivative as a given function, of a given function. Then understand the relationship among the displacement, velocity, and acceleration. Last, analyze the pattern of displacement, velocity, and acceleration, given a displacement function of an object. Okay, so first of all, let's have a look at the concept of second derivatives. The second derivative of a function is simply the derivative of the function's derivative. So the derivative of the derivative is called the second derivative. Remember, the derivative of a function is also a function, right? Therefore, you can also differentiate the derivative of the function. So let's consider, for example, the function fx equals x cubed plus 2x squared. Its first derivative is f prime x equals 3x squared plus 4x, right? That's the first derivative, or simply called derivative. To find its second derivative, f prime prime, we need to differentiate f prime. When we do this, we find that the second derivative of fx with respect to x equals 6x plus 4, right? Second derivative is just the derivative of the first derivative. Therefore, if you differentiate 3x squared plus 4x, then we will get the second derivative, which is 6x plus 4. So f prime prime x is called the Lagrange notation for the second derivative. Note that we have a second type of notation, which is called Leibniz notation, right? So Leibniz notation for second derivatives is that one. D squared y by dx squared. Or you can also say it's the second derivative of y with respect to x. For example, the Leibniz notation for the second derivative of x squared plus 2x squared, x cubed plus 2x squared is written in that way. So d squared over d squared by dx squared of x cubed plus 2x squared, okay? So basically, this is the concept of the second derivative. Any questions? Any questions? So just remember, the second derivative is the derivative of the derivative. Yes. Okay, next, let's have a look at the interpretation of second derivative. Given the function fx, if fx is differentiable, then the derivative f prime x is the slope of a tangent line of the graph of fx, right? At any x value, or in other words, f prime x measures the instantaneous rate of change of fx with respect to x at any x value. So what is the meaning of the second derivative? The meaning of the second derivative is if the derivative of fx, which is f prime x, is also differentiable, then the second derivative, f double prime x, is actually the slope of the tangent line of the graph of f prime x, right? At any x value. Or in other words, f double prime x measures the instantaneous rate of change of the derivative f prime x with respect to x at any x value. Okay, so let's have a look at an example. Okay, let's see the example here. The original function fx is given by this expression, y equals 1/3 of x cubed minus x squared minus 3x plus 4. So the graph of this function is illustrated here. It's a polynomial function, right? You understand? We have learned this in advanced function. The graph of this function is a polynomial and looks like this, right? And if we find its first derivative, the first derivative of this function is y equals x squared minus 2x minus 3. And if we graph the first derivative of this function, the first derivative looks like this, which is a parabola. So why is this first derivative has this shape? Because as you can see here, before the key point x equals 1, this function keeps increasing, right? Before x equals 1, this function keeps increasing, right? Therefore, the instantaneous rate of change of this function is positive, right? And at this point, this function stops increasing. Therefore, at x equals 1, the first derivative of this function equals 0. And after that, the slope of the tangent is negative until x equals 3, as you can see here. Therefore, the first derivative of this function actually describes the instantaneous rate of change of the original function at any point x. You understand? And then if we find its second derivative, which is y equals 2x minus 2, actually, the second derivative describes the instantaneous rate of change of the first derivative, y equals x squared minus 2x minus 3. And similarly, you can see that for the first derivative, if we only consider this function here, this function keeps decreasing until the point x equals 1, right? Therefore, the second derivative, which is a derivative of the first derivative, is a negative number until x equals 1. And after that, the derivative is increasing until all the way up to positive infinity. Therefore, after x equals 1, the derivative of the first derivative, which is the second derivative, will be a positive number. You see that? So just remember, the first derivative measures the instantaneous rate of change of the original function at any point. Then the second derivative measures the instantaneous rate of change of the first derivative. Understand? All right, let's see a specific example here. So determine f double prime at x equals 2 for the function fx equals 3x squared plus 2 times 1 minus x. Okay, I'll give you 1 minute to think about this question. All right, let's have a look at the solution. First of all, if you want to find the second derivative, you need to find the first derivative, right? The first derivative of this function is we can apply the product rule, right? First derivative is negative 9x squared plus 6x minus 2. Then the second derivative is just the derivative of the first derivative, which gives us negative 18x plus 6. Therefore, if you want to find the second derivative at x equals 2, you can simply put x equals 2 into the expression of the second derivative. And the second derivative at x equals 2 equals negative 30. Understand? You have any questions? No? Okay, so let's have a look at the application of second derivative in the real world. A typical example is the relationship of displacement, velocity, and acceleration. So let's have a look at their relationship here. First of all, let's have a look at the definition in verse for displacement S, velocity V, and acceleration A. So in convention, we'll use SVA to denote displacement, velocity, and acceleration. So this distance, the displacement is defined as the distance an object has moved from the origin over a period of time. Note the displacement can be either positive or negative. The velocity is the rate of change of displacement with respect to time, t. The acceleration is the rate of change of velocity with respect to time t. Therefore, they have the following relationship. Displacement can be expressed as a function of t, right? An object can have different displacement at different times. The velocity is the first derivative of s with respect to t. Therefore, vt equals ds by dt. The acceleration, because it measures the rate of change of the velocity. Therefore, it's the derivative of the velocity with respect to t, right? So note here, the dv by dt is actually ds by dt. Therefore, the acceleration is also the second derivative of s with respect to t. Understand? And typical units. Typical unit for displacement is meters. Typical unit for velocity is meters per second. For acceleration, this is meters per square second. So also, you should be careful with the difference between speed and velocity. Speed is a scalar quantity. It describes the magnitude of motion, but does not describe direction. Velocity, on the other hand, is a vector quantity. It has both magnitude and direction. The answer in velocity problem will be either a negative or positive value. The sign indicates the direction the object is traveling. That is, the original position of the object is considered the origin. One direction from the origin is assigned positive values, and the opposite direction is assigned negative values, depending on what makes sense for this question. Any questions? Okay, let's see a specific example to illustrate this concept. Okay, let's have a look at this question here. A construction worker accidentally drops a hammer from a height of 90 meters while working on the roof of a new apartment building. The height of the hammer, S in meters, after t seconds is modeled by this function. S equals 90 minus 4.9 t squared, where t is greater than or equal to 0. There are 6 questions. I'll give you 5 minutes to have a look at the following questions. All right, let's have a look at the solutions. First question. Average velocity is the average rate of change of s with respect to t, right? So according to the definition, that's the delta s over delta t. But delta t is from 4 to 1. So 4 minus from 1 to 4. So delta t is 4 minus 1. Delta s is s4 minus s1. So you can just simply put t equals 4 and t equals 1 back to that st equation, right? So the average rate of change is negative 73.5 over 3, which gives us negative 24.5. Therefore, the average velocity, the hammer between 1 second and 4 seconds is negative 24.5 meters per second. Okay, question B. Explain the significance of the sign of your result in part A. So in this type of problem, the movement in the upward direction is commonly assigned positive values. So you can also check that when t equals 0, when t equals 0, s equals 90, right? Therefore, the upward position is a positive position. Because we know at t equals 0, the hammer is 90 meters above the ground. Therefore, the negative answer indicates that the motion of the hammer is downward, which is opposite to your positive direction. And the amplitude of this vector is 24.5. That means the speed, which is a scalar of the hammer, is 24.5 meters per second, right? Okay, question C. We know Vt equals the derivative of st with respect to t, right? So we need to differentiate st, which gives us negative 9.8 t. Remember, we have learned how to differentiate a polynomial function, right? So if we differentiate the polynomial function 90 minus 4.9 t squared, you will get negative 9.8 t. Then this is a instantaneous rate of change of this hammer at any t, right? So if you want to find the instantaneous rate of change at t equals 1 and t equals 4, simply put t equals 1 or t equals 4 to the derivative of st, which is vt. Then we know the velocity of the hammer at 1 second is negative 9.8 meters per second. And at 4 seconds, it is negative 39.2 meters per second. Once again, the negative answers indicate downward movement. Any questions? No? Okay, next one, question D. The hammer hits the ground once the displacement is 0. So remember, the displacement is also a vector, right? If the displacement is 0, we know the hammer hits the ground. Therefore, we can solve st equals 0 in terms of t. Solve for t, right? And that means 90 minus 4.9 t squared equals 0. And the solution is t either negative or positive 4.29. Because t is greater than or equal to t, therefore we only keep the positive answer. Therefore, at approximately 4.29 seconds, the hammer will hit the ground. Okay, question E. The impact velocity is the instantaneous velocity when the hammer hits the ground, right? So we know the t equals 4.3 seconds. So we can just put 4.3 to the equation of v to get the instantaneous rate of change or the instantaneous velocity of this hammer, right? Okay, so ask me the question F determines the acceleration function. Okay, now let's find its acceleration functions. So note acceleration is the derivative of velocity, right? So we know acceleration function. Let's write it here. A t equals dv by dt, or d square s by dt square, which is the second derivative of s with respect to t, right? Because you have already solved dv by dt is negative 9.8 t, right? So ds by dt, which is v t, equals negative 9.8 t. Therefore, we know dv by dt is negative 9.8, which is a constant number. The unit is meters per square seconds. So this is the acceleration of this hammer at any time t. So notice something here. This is acceleration of any free fall object, right? Okay, any questions? Okay, this means at any time t, the instantaneous rate of change of the velocity is negative 9.8 meters per second. Okay, so other takeaways of this problem is, in general, if the acceleration and velocity of an object have the same sign at a particular time, then the object is being pushed in the direction of the motion, and the object is speeding up. If the acceleration and velocity have opposite signs at a particular time, then the object is being pushed in the opposite direction to its motion, as it is, and this is slowing down. Therefore, we have the following conclusion. An object is speeding up at time t if vt times at is greater than 0. That means vt and at have the same signs. Whereas an object is slowing down at any time t if vt and at, if at times at is less than 0. That means the signs of vt and at are different. Understand? Okay, so next, let's have a look at another example. Relate velocity and acceleration. So the position of a particle moving along a straight line is represented by this function. St equals t cubed minus 12t squared plus 36t, where distance s is in meters, time t in seconds, and t is greater than or equal to 0. This graph of position, the graph of this position function is given. Sketch the graph of the velocity and acceleration functions, and then determine when the particle is speeding up and slowing down. How does this relate to this slope of the position function? Okay, I'll give you 3 minutes to have a look at this solution here. Can you sketch the graph of the velocity and acceleration function? Remember, the velocity is just the instantaneous rate of change of displacement, right? And acceleration is the derivative of the velocity. All right, let's have a look at the solution. Okay, first of all, in order to graph this velocity or acceleration, it's better to find the expression of such functions, right? So if we know s equals t cubed minus 12 t squared plus 36, recall that velocity is the derivative of s with respect to t, right? Therefore, the function of the velocity at any time t is given by ds by dt, which is 3t squared minus 24t. Then acceleration at time t is derivative of v respect to t, or the second derivative of s with respect to t, right? This is given by 60 minus 24. Then if you know the expression of these two functions, it is very easy to graph them on the 2D Cartesian plane, right? So let's have a look at the graphs. First, this is the original graph, which is st with respect to t, right? Then if we know the velocity with respect to t is it has the expression like this. This is actually a quadratic function, right? We know quadratic function is either opening up or down. So actually you can correlate these two graphs. As you can see here, there are some critical points at x equals 2 and x equals 6, right? At x equals 2, the instantaneous rate of change or the instantaneous velocity equals 0. So that corresponds to the parabola at x equals 2. As you can see here, the v here is 0, right? Before that, the velocity is a positive number, but it's getting smaller and smaller, right? This corresponds to the trend in the second graph, which is Vt. So we can analyze similar trend between t equals 2 and t equals 6. And after t equals 6, as you can see here, the instantaneous velocity keeps increasing, right? This corresponds to the trend in the second graph, which is Vt. Also, because the acceleration is the derivative of the velocity with respect to t, you can also correlate these two functions in their graphs. So as you can see here, in the velocity graph, there is a critical point at x equals 4, right? At this point, the instantaneous rate of change of the velocity equals 0. Therefore, the acceleration is 0 at x equals 4. Before that, the instantaneous rate of change of the velocity is always negative. But this negative number keeps increasing until 0, which corresponds to the trend in the third graph, velocities graph. And after this critical point at x equals 4, the slope of the parabola, which is the instantaneous rate of change, or which is instantaneous velocity, keeps increasing until all the way up to the positive infinity. This corresponds to the trend in the acceleration graph after t equals 4, right? Any questions? Okay, then let's consider question B. The graph of Vt changes sign at the intercept t equals 2 and t equals 6. The graph of At changes sign at the intercept t equals 4. The signs of Vt and At are easily observed by determining whether the respective graph lies below or above the t-axis. Consider the following 4 time intervals: 0 to 2, 2 to 4, 4 to 6, and 6 to 8. If you want to decide the motion of the particle, remember we need to decide the sign of the product of Vt and At, right? So these 4 points divide the whole region into 4. In each of the 4 regions, the sign of the Vt times At might be different, right? So we can use the table to summarize the signs of the product of Vt by At. So in the first interval from 0 inclusive to 2 exclusive, we know the sign of Vt is positive, At is negative. Therefore, Vt times At is negative. Therefore, we know the motion of the particle is slowing down and moving forward. And description of the slope of St is positive slope that is decreasing, right? Any questions? Then we can analyze the other intervals using the same method. So for example, in the second interval from 2 to 4 exclusive, we know the Vt is now negative and At is also negative, right? Therefore, Vt by At is positive. Then the motion of the particle is speeding up and moving in reverse. Next, in the interval from 4 to 6, because Vt is negative, At is positive, therefore the product of Vt and At is negative. Then the particle is slowing down and moving in reverse. That means moving in the negative direction. In the last interval from 6 to 8, we know the speed is, the velocity is positive, the acceleration is also positive. The product of velocity and acceleration is also positive. Therefore, the particle is speeding up and moving forward. Therefore, we know the particle is slowing down between 0 seconds and 2 seconds, and again between 4 seconds and 6 seconds. The particle is speeding up between 2 seconds and 4 seconds, and after 6 seconds. Any questions? Okay, if no questions, let's consider another example. Can you analyze and interpret a displacement time graph? The graph below shows the precision function of a motorcycle. Describes the slope of the graph in terms of being positive or negative, increasing or decreasing. Over the interval between consecutive pairs of points, beginning at origin. For each interval, determine the sign of the velocity and acceleration by considering the slope of the graph. Okay, I'll give you 3 minutes to consider this question. Okay, have you finished? Well, let's have a look at the solution here. So we can organize the analysis of this situation in the following chart. First column lists all the intervals from A to 0, from 0 to A to B, B to C, C to D, D to E, and E to F. Second column states the slope of the graph. So from 0 to A, we know the slope is always positive, right? And the slope is also increasing. That corresponds to the velocity is also positive and acceleration is also positive. Second interval A to B, we know the slope is still positive. That corresponds to the positive velocity, but it is decreasing to 0 at B, right? Therefore, we know the acceleration is decreasing, is a negative number. From B to C, we know the slope is negative and keeps decreasing from 0 to a very large negative number. That corresponds to velocity From B to C, the slope is negative, and it is decreasing. That corresponds to negative velocity and negative acceleration. C to D, the slope of the graph is negative, and it is increasing. That corresponds to negative velocity and positive acceleration. From D to E, the slope is 0. And horizontal, this is a horizontal segment, right? There is no instantaneous rate of change is always 0 in this direction, in this segment. Therefore, we know the velocity is 0 and acceleration is also 0. The last interval from E to F, the slope is always negative and it is decreasing. That corresponds to negative velocity and negative acceleration. Okay, so let's have a look at another example. Given the displacement function y equals st below, sketch the velocity function y equals vt and the acceleration function y equals at in the same graph. Okay, I'll give you 3 minutes to think about this question. Okay, let's have a look at the solution. First of all, there are two critical points for the ST, right? So first of all, ST equals okay, there is no instantaneous rate change at this point and this point, right? Therefore, we know at these 2 points, the velocity must be 0. And before this point, you can see the instantaneous rate of change of the S is negative and keeps increasing, right? So therefore, we have a trend like this. And after that, the slope is positive. And then first increasing and then decreasing all the way back to 0 again. So basically, it will have a trend like this. Then after that, this instantaneous velocity is negative and keeps decreasing. So the y equals vt will have a trend like a parabola that is opening down, right? So the acceleration function is the derivative of the vt, right? So note here, the derivative of vt is 0. Therefore, at this point, the acceleration is 0. Before that, the slope of the instantaneous rate of change of v is positive and keeps decreasing until 0. And after this point, the instantaneous rate of change of v is negative and keeps decreasing. So the acceleration might look like a straight line with a negative slope. Okay, any questions? Again, this is only a rough sketch of the corresponding points because we don't know any other information. All right, if you don't have any questions, let's give it a quick recap of the key concepts of today's lesson. First, the second derivative of a function is determined by differentiating the first derivative of the function. Then, for a given position function st, its velocity function is vt, or the derivative of st, and its acceleration function is at, or the derivative of vt, or the second derivative of st. Then when vt equals 0, the object is at rest or stationary. There are many instances where an object will be momentarily at rest when changing directions. For example, a ball thrown straight upward will be momentarily at rest at its highest point and will then begin to descend. Next, when vt is greater than 0, the object is moving in the positive direction. Next, when vt is less than 0, the object is moving in the negative direction. When at is greater than 0, the velocity of the object is increasing. When at is less than 0, the velocity of an object is decreasing. Last, an object is speeding up if vt times at is greater than 0, and slowing down if vt times at is less than 0. Okay? Any questions? All right, so last, let's revisit today's learning goals. So now you should be able to understand the concept of second derivatives, evaluate the second derivative of a given function, understand the relationship among the displacement, velocity, and acceleration, and analyze the pattern of the displacement, velocity, and acceleration given a displacement function of an object. Okay, so basically this is today's lesson. Any questions? No questions? Class dismissed.